Alright, now we're going to take that same alternator that we talked about in our last example, and to keep things simple, we're going to feed that same a load with the same current value, still Y connected, but now this load is going to have a power factor of 0.9 lead. So our Z and our everything, nothing about the alternator is changed. So our Z value is still happening at 83.18 degrees, but now our E, our V line, because we're leading, is going to be 60 amps, and our power angle is going to be still 25.84 degrees, but now it's going to be negative 25.84 degrees, which means that our E generated, oh, we got a heck of a glare here. There we go. Our E generated is going to be, we still got the same amount of current, so this is still 96 volts. This is still 277 volts, because that's what we're going to set our generator to, or our alternator to run at. So if we go 96 at 83.18 plus 277 at negative 25.84 gives us an E generated value of 261.94. At negative 5.567, so it's going to be happening right down in here somewhere, right? 5 degrees off of our reference point. Okay, so with our lagging voltage, when we had this connected to a lagging, still the same current, but when our load was 0.9 lagging, we needed to generate 338.59 volts to give us our 277 volts of output voltage. However, now that we've got a leading power factor load, we don't need to generate near as much voltage, because that capacitor, or that capacitive load, the leading power factor load, it's taking care of some of the voltage drop that would be normally across our XL of our alternator windings. So we don't need, we're going to end up basically, what it means at the end of the day is we don't have to, there's a 96 volt drop across our alternator windings, but some of that voltage drop is fed from the capacitance of our load. That's why our generated voltage actually is lower than our terminal voltage, because that, with the leading power factor load, it's feeding back in, and that's satisfying that inductive volt drop within the alternator.